Hello everyone. In this section, we will introduce the basic structure and equivalent circuit of amplifier circuits in electronics. Since this topic is a little long, it will be divided into two videos. This video will cover the signal part. Let's get started. Go. The structure of an amplifier circuit can generally be divided into three parts. The first part is the signal source. The second part is the amplifier. The third part is the load. The input terminal of the amplifier is connected to the signal source, and the output terminal is connected to the load. For example, sound can be converted into an electrical signal by a microphone. The amplifier then amplifies this electrical signal and sends it to the load for playback. Therefore, for an amplifier, the input terminal is the terminal that receives the signal, and the output terminal is the terminal that sends out the processed signal. First, we will introduce the signal source part. An electrical signal source can be represented by a voltage signal. It can also be represented by a current signal. If a voltage signal source is used, its equivalent circuit model is a voltage signal source, Vs, connected in series with a signal resistance, Rs. This is called the Thevenin equivalent circuit. If a current signal source is used, its equivalent circuit model is a current signal source, Is, connected in parallel with a signal resistance, Rs. This is called the Norton equivalent circuit. Any unknown signal source can be modeled as both a Thevenin equivalent circuit and a Norton equivalent circuit. In other words, the Thevenin equivalent circuit and the Norton equivalent circuit can be converted into each other, so they are equivalent circuits. How do we obtain the circuit model of a signal source from an unknown signal terminal? To summarize it in one simple sentence, use an open circuit to find the voltage and use a short circuit to find the current. Using an open circuit to find the voltage means leaving the output terminal of the signal source open. Then, measure or calculate the voltage signal at the output terminal. This is the open circuit voltage signal source, Vs. Using a short circuit to find the current means grounding the output terminal of the signal source. Then, measure or calculate the current signal flowing out of the output terminal. This is the short circuit current signal source, Is. Then, divide the open circuit voltage source, Vs, by the short circuit current source, Is. This gives the signal resistance, Rs. Once we have the open circuit voltage source, Vs, the short circuit current source, Is, and the signal resistance, Rs, we can obtain either the Thevenin equivalent circuit or the Norton equivalent circuit. You can try calculating this yourselves. When the output terminals of the two equivalent circuits are open-circuited, their open circuit voltages are both Vs. For the Norton circuit, the open circuit voltage equals Is multiplied by Rs. According to the equation shown on the slide, this is equal to Vs. When the output terminals of the two equivalent circuits are short-circuited to ground, their short-circuit currents are both Is. For the Thevenin equivalent circuit, the short-circuit output current is Vs divided by Rs, which is equal to Is. Therefore, the Thevenin and Norton equivalent circuits are equivalent to each other and can be converted into each other. In addition to equivalent circuits, we will next introduce the mathematical form of signals. You should know that an arbitrary waveform signal can be formed by combining many sine waves with different amplitudes, frequencies, and phases. Therefore, if your circuit can operate the same way for all amplitudes, frequencies, and phases, then a single sinusoidal signal can usually be used as the representative signal. This type of amplification is called linear amplification. Linear amplification means amplifying the original waveform by the same factor everywhere. Therefore, the amplified waveform is not distorted. However, if different amplitudes or different frequencies have different amplification gains, then the amplified signal waveform will be distorted because the original waveform can no longer be reconstructed. For example, the input signal shown in the diagram has three peaks with different amplitudes. After passing through an amplifier with a gain of 3, if the largest amplitude is amplified by less than 3 times, while the other two amplitudes are amplified by exactly 3 times, then a distorted output signal waveform will be produced. Next, we will introduce the circuit symbol of an amplifier. The diagram shows the symbol of a two-port signal amplifier. It is a triangular shape and the arrow represents the direction of signal transmission. Next, we will introduce the types of amplifier gain and their units. First is voltage gain, AV. Voltage gain is the output voltage, VO, divided by the input voltage, VI. Its unit is volts per volt, or V per V. Next is current gain, AI. Current gain is the output current, IO, divided by the input current, II. Its unit is amps per amp, or A per A. Finally, we introduce power gain, AP. Since power equals current multiplied by voltage, the output power, PL, is the output current, IO, multiplied by the output voltage, VO. The input power, PI, is the input current, II, multiplied by the input voltage, VI. Power gain is equal to output power divided by input power. Therefore, power gain is also equal to current gain multiplied by voltage gain, and its unit is watts per watt. Gain also has another unit called decibels. For voltage gain and current gain, first take the absolute value, then take the base 10 logarithm, and then multiply by 20. The resulting value is expressed in decibels. For power gain, first take the absolute value of the power gain, then take the base 10 logarithm, and then multiply by 10. The resulting value is expressed in decibels. It is also equal to 1/2 of the sum of the voltage gain in decibels and the current gain in decibels. You can observe that when gains are expressed in decibels, 0 decibels means the amplification factor is 1. When the amplification factor is less than 1, the decibel value is negative. When the amplification factor is greater than 1, the decibel value is positive. In other words, the sign of the decibel value tells us whether the output signal is amplified or reduced compared with the input signal. After discussing signal amplification in amplifiers, we will next look at power calculations in the whole circuit. When an amplifier is used, the input terminal is connected to the input signal, VI, and the output terminal is connected to a load. The load is usually simplified as an impedance. Here, we first use a resistor as an example. In addition to signal input and signal output, the circuit itself must be supplied with a DC bias in order to start and operate. This is just like any electrical appliance. It must be plugged into a power source before it can turn on. Therefore, a circuit may have one or more DC bias sources. The slide shows an example using two DC bias sources, VCC and negative VEE. DC bias sources also generate DC currents, and these also contribute to the power when the circuit is operating. Therefore, the power delivered by the DC bias sources to the circuit, PDC, is VCC multiplied by ICC plus VEE multiplied by IEE. The total input power is the DC bias power, PDC, plus the input power of the AC signal, PI. This must be equal to the load power, PL, plus the dissipated power, P dissipation. In other words, any power that is not delivered to the load is counted as dissipated power. Finally, the amplifier efficiency, eta, can be calculated. Amplifier efficiency equals PL divided by PDC. An important concept here is that signal amplification does not appear out of nowhere. It requires energy or power. Therefore, signal amplification is achieved through the energy supplied by the DC bias. From this, we can understand that signal amplification is limited by the DC bias supply. It cannot have unlimited energy like the androids in the manga Dragon Ball. As we have just explained, signal amplification depends on the energy supplied by the DC bias. Therefore, an amplifier does not amplify signals without limit. There is always a maximum output limit. This is called amplifier saturation. As shown in the figure on the right, The x-axis is the input voltage signal, and the y-axis is the output voltage signal. The relationship between the two is called the transfer characteristic, and the slope of the curve is the voltage gain, AV. From the figure, we can see that the output signal has an upper limit L plus and a lower limit L minus. Therefore, when the amplitude of the input signal exceeds L plus over AV or L minus over AV, the output signal reaches the output limit and will no longer increase. As shown on the slide, when the input signal is the red curve, the output voltage is the green curve. Because the output signal does not exceed the saturation output voltage of the circuit, it can be linearly amplified normally, and the signal shape is not distorted. When the amplitude of the input signal increases to the purple curve, the maximum amplitude of the input voltage reaches L plus over AV and L minus over AV. Then, the output voltage, shown as the brown curve, just reaches the saturation output voltages, L plus and L minus. If the amplitude of the input signal continues to increase to the dark brown curve, the maximum amplitude of the input voltage exceeds L plus over AV and L minus over AV. Ideally, the output voltage should be as shown by the orange curve. However, because the maximum amplitude of the orange output curve exceeds the saturation output voltages, L plus and L minus, the portions beyond the limit will not be amplified. Instead, they will reach saturation. Therefore, the final output curve is the light blue curve shown on the right. Therefore, in order to avoid distortion in the amplified signal, the output voltage, VO, must lie between L minus and L plus. Therefore, the range of the input signal is limited to between L minus over AV and L plus over AV. Finally, we will introduce the notation conventions for electrical signals. In general, electrical signals can be divided into two types: DC signals and AC signals. For DC signals, a DC voltage is represented using an uppercase letter V together with an uppercase letter as the subscript. For example, uppercase V with uppercase D as the subscript is written as VD. Similarly, for DC current, the notation uses an uppercase letter I together with an uppercase letter as the subscript. For example, uppercase I with uppercase A as the subscript is written as IA. For AC signals, an AC voltage is represented using a lowercase letter v together with a lowercase letter as the subscript. For example, lowercase v with lowercase d as the subscript is written as VD. Similarly, for AC current, the notation uses a lowercase letter I together with a lowercase letter as the subscript. For example, lowercase I with lowercase a as the subscript is written as IA. For a complete total signal, the signal is formed by superimposing a DC signal and an AC signal. Therefore, the notation for the total signal uses a lowercase main letter with an uppercase letter as the subscript. The total voltage signal is written as lowercase v with uppercase d, and the total current signal is written as lowercase I with uppercase a. In addition to the notation categories for DC and AC, the amplitude of a small signal sine wave is represented using an uppercase main letter with a lowercase letter as the subscript. For example, uppercase V with lowercase d represents the voltage sine wave amplitude. Similarly, uppercase ein with lowercase a represents the current sine wave amplitude. If you want an easy way to remember this, start with the simple cases. When both the main letter and the subscript are uppercase, it represents a DC quantity. When both are lowercase, it represents an AC quantity. A lowercase main letter with an uppercase subscript represents the total signal, and this one needs to be memorized. The remaining combination, an uppercase main letter with a lowercase subscript, represents the sine wave amplitude. This is not used very often in electronics, but it is often seen in electromagnetics. Finally, using the current signal diagram as an example, the DC current is marked with uppercase I and uppercase A as the subscript. The AC current is marked with lowercase I and lowercase a as the subscript. The total current is marked with lowercase I and uppercase A as the subscript. The AC sine wave amplitude is marked with uppercase I and lowercase a as the subscript. These labels are provided to help you understand and remember the notation. That concludes the signal part of the introduction to the basic structure and equivalent circuit of amplifier circuits. In the next class, we will continue with the amplifier circuit part of the basic structure and equivalent circuit of amplifiers. See you next time. Bye-bye.